Cool. So, hello everyone. Welcome to NISER Astronomy's second webinar, alumni webinar from Biprateep here today. He's my personal favorite senior, so to say, and a good programmer and a great storyteller too. So, I hope you enjoy his talk on mapping the universe using sky surveys. Over to you, Biprateep.
Hey everyone. As Santap mentioned, I am Biprateep. I graduated a couple of years ago.
Home Priya, can you please? Thank you. Yeah.
Okay. Yeah, I was getting a bit of feedback. Okay. Yeah, I graduated a couple of years ago, and I've been working at University of Pittsburgh for the last 2 years. So this talk doesn't have a lot of science content in it because it's quite hard to teach new science in 1 hour, but rather what I want to do is tell you about what's going on in one of the fields of astronomy right now, and how and why you may join a research program in some related fields. And feel free to interrupt me with your questions if you have something immediately, or if you prefer to ask anything at the end. Do whatever you like. And in the end part will be a discussion on PhD programs, mainly focused on programs outside the US. And I'm no expert on this topic, but I'll just try to share whatever I learned while applying myself. Uh, so, to begin with, astronomy, as you might have known, is probably the oldest observational science. The only requirement for people to do astronomy was to just look up, and you could see stars and other stuff. And these things, the sky changes with time in a periodic fashion. And because of this, these were also linked with seasons. So people thought that somehow the appearance or disappearance of some stars will affect the seasons and govern their lives indirectly. So even thousands of years ago, people made it a point to catalog what they see in the sky and basically write them down. And this process of cataloging everything you see on the sky is basically what a sky survey is. You just note down everything that you see. Um, so people have been doing it for a couple of thousand years. Uh, but even if we consider that modern science began with Newton, then what have we learned about the universe in general over the last 400 years? Uh, so, all known physics can be considered to be this tiny sliver, tiny blue sliver in the pie chart. Um, what we do not know is a lot. Um, what I mean by this pie chart is if you look in the sky and just count somehow the things that we can see and also has mass, those are the things that we understand. Uh, by seeing, I mean things which emit or absorb light or somehow interacts with light. Uh, there is a lot of stuff out there which we cannot see, but we can indirectly measure its presence by measuring its mass. And then there's a lot of other stuff which we frankly have no clue about. So if you tally the total energy that's causing the universe to behave the way it is now, you'll find that everything we know just contributes to like 5% of the behavior, of the large scale behavior of the universe. These comprises of all atoms, molecules, you, me, an elephant, everything. So there's a lot of other stuff called dark matter, which we cannot see, but has mass. And we can indirectly measure the mass. And that contributes roughly to 27% or 30% of the behavior of the universe in large scales. And then there's the big chunk of it, which we call dark energy, because it's some kind of energy, but we just do not know. We are still in the dark about it. So we just named it dark energy, which is the major dominant factor of controlling the universe's evolution right now. So how can we explore it using astronomy? So as I had mentioned previously, people used to look at the sky and catalog stuff. Currently, we do the same thing, but in a bit more modern way. What we would do is take a telescope and point it to the sky and record everything that we see. And this is what a modern sky survey looks like. You take a telescope, fix a camera at the end of it, and picture whatever is visible by the telescope. This process is called photometry. So this is basically equivalent to taking a picture of the sky using a camera. Generally, what people do is they do not just simply point a camera to the sky. Rather, what they do is divide the whole visible spectrum of wavelengths into smaller chunks and grab pictures of the sky in these chunks of wavelengths. And you'll have the same picture of a galaxy or a star or whatever it is in different chunks of wavelength. So as you can see here, I just showed how the same galaxy looks like in different wavelength bands, where U is ultraviolet, green, red, infrared, and far infrared. And if you notice carefully, the galaxy does look slightly different in different chunks of wavelength. So just going and looking at stuff and pointing things in the sky will give you a two-dimensional map, because you just know the location of everything on this flat sky. Recently, a survey called Legacy Survey was conducted, and which made the largest ever two-dimensional map of the universe. And they have a really cool interface where you can just treat it as Google Earth, but universal version, where you can just roam around the whole sky and look at different galaxies and all. It's an interactive map, and you can check it out at legacysurvey.org. So now the thing is, we now have a two-dimensional map. How do we add the third dimension? The third dimension is the distance from us, how far something is from us. So this is more or less an observational fact that we see that every other extragalactic object is going away from us. We say this happens because the universe is expanding, or space itself is expanding, and hence everything which is contained inside the space is going far away from everything else. So if a light wave is traveling through that space and the space itself is expanding, the light wavelength expands with the space itself. And the longer the light has to travel through that space, the more time it has to expand. So that means if a light is coming from a far off object, the wavelengths will get expanded more than something which is closer by. So if we can measure how much the light wavelengths have expanded, this can act as a proxy for how far an extragalactic object is. And we do the exact thing using a process called spectroscopy. In its very simplest form, spectroscopy is basically equivalent to collecting the light from an object, a galaxy, pass it through a prism so that we can split the light into its different components. And generally, light from galaxies is not just a plain spectrum of all the colors. It has all the colors, but there are certain colors or certain wavelengths of light which are more prominent than the others. We call them emission lines. So if the wavelengths have expanded, then the location of these emission lines will change. So we compare these locations of these lines to what should have been the case in a rest frame, in a laboratory, for example. And by this comparison, we can measure the redshift of an object. And assuming we know everything else about the universe, which we don't, but if we assume that, then we can convert this redshift to a distance. And hence we can get the third dimension. So now we have this three-dimensional map of the universe. So what can we do with it? I'll just go by a whirlwind tour of different science cases which we can do using these surveys. This is by no means exhaustive or comprehensive. There's a lot of other stuff that you can do, but I'll mention the things which are currently pretty hot. So if you have been keeping track of the news, then because of the last Nobel Prize, a term called baryon acoustic oscillation was probably quite hot in the news. We can study those. So in its very simplest form, what is this fancy word stand for? So when the universe started, everything began with this hot soup of stuff in it, where ionized atoms, dark matter, everything else was in this whole soup. So there were two dominant forces acting. There's gravity, which will try to collapse everything or coalesce everything. And then there's this electromagnetic forces which oppose that or create a pressure. So if you imagine there are two forces, one trying to pull this soup in a center, and there's something else which is pressure, which is trying to push everything away, you get this oscillatory motion, which is basically similar to sound waves. And these sound waves traveled through this primordial soup, and sound waves have this compression and rarefaction regions. Compression corresponds to a region where there is more matter. A rarefaction is a region where there's less matter. Just like when we talk, we compress the air, and this compression moves in a periodic fashion to the air and goes to someone else's ear, and we can hear stuff. So this is the same thing. These are sound waves which traveled in this primordial soup. And slowly, when things cooled down and different galaxies and other structures formed, galaxies preferably formed in those regions where there was more matter, that is the compression regions for those sound waves. And observing these oscillations can tell us a lot about how the universe began or evolved long ago. So how can we observe these oscillations now using sky surveys? So as I said, using a sky survey, you now have with this three-dimensional map of this universe, you have locations of other galaxies in this three-dimensional space. What you can do is calculate the distance or the separation between any two pairs of galaxies or every two pairs of galaxies that you can see. You have these separations between all two possible pairs of galaxies, and you just make this plot where on the x-axis you just write down the separation between two galaxies, and the y-axis you just write down the probability of finding a galaxy at a given separation. So if I find 10 galaxies which are 10 kilometers apart, I just write, okay, there are 10 galaxies 10 kilometers apart. Then there are 20 galaxies which are 20 kilometers apart. There are 40 galaxies which are 30 kilometers apart, so on and so on and so forth. So at the lower end of the spectrum, we see that generally gravity dominates and tries to keep everything together, and there's a lot of galaxies which are close apart. And if gravity was the only force dictating the evolution of the universe, then we would think that, okay, since there's more time to pull everything together, there will be more galaxies which are very close by, and there will be fewer galaxies which are very distant from one another. But what we see is this tiny bump that galaxies are more likely to be found at a separation which corresponds to roughly 460 million light years. And this shows that these opposing forces of gravity and pressure due to electromagnetic forces had played a role in the formation of a structure in the universe. This tiny bump is what people tend to say what a signal from baryon acoustic oscillations is, that there's a preferable distance in which galaxies are separated. And this distance corresponds to the wavelength of the sound that traveled in this primordial soup. And galaxies preferably formed at the compression regions because there was more matter there. And last year's Nobel Prize was awarded to Jim Peebles, who made the first theoretical foundations for this thing. And hence, since this was pretty recently in news, I kept it as the first topic. Though it was theoretically hypothesized in 1970s or so, it was observed using the Sloan Digital Sky Survey for the first time in 2005, which cataloged about a couple of million galaxies in this three-dimensional space, and then this did these things. This plot is from a paper, and the x and y axis do not directly correspond to what I label them as, but they are synonymous to this fact. I just, to make things simpler, have relabeled them. Another thing that you can see if you have these images of the whole sky is that study gravity, and using that measure, for example, even the expansion rate of the universe. So we now know that gravity bends light, and generally Newtonian gravity cannot explain how gravity can influence a massless object like light. But Einstein's general relativity could explain how gravity can affect light. And when we look at the sky, and if there's a situation where there's a bright object behind a very massive object, we can see that the light from that bright object behind something is bent. In a very simple situation, if something is behind another thing, we cannot see the small thing which is behind a big thing. But since gravity affects light, it acts as this lens which bends light, and we can see the image of something even though it's behind a massive object. And quasar is a point source of very bright light behind a galaxy. And if you look at the picture, you'll see that you can see these 4 dots surrounding this bright object, and this is basically what is called gravitational lensing. By measuring these kinds of phenomena, we can not only study how gravity works in large scales, but given the fact that the light has traveled different distances to come at different locations in this picture, the same light has come to 4 different locations. We can measure for example, time delays between these objects, to see how the universe has evolved over the period when the light traveled. And we can do a lot of stuff by studying lensing. This phenomenon is called lensing, and that's one other thing that you can do. Um, Again, that I said, when you have this map of the universe, we can just plot it out in three-dimensional space. And as shown in this picture, each point or each dot in this picture is the location of a galaxy as seen by the Sloan Digital Sky Survey. The circular region, the circular axis corresponds to yep. Dukisham Bhai's question is that he wanted to know. So his question is, what is the distance till which photometry and spectroscopy is applicable? And if something is coming from, if light is not coming from okay, he has three questions. So the first question is, what is the distance to which we can apply photometry and spectroscopy? And it entirely depends on the size of the telescope that you have. For example, this image was created using the Sloan Digital Sky Survey, and it could see up to a redshift of 0.1, and it was a 2.5 meter big telescope. As I'll show soon, there are bigger telescopes which are starting to do similar things, and they can see up to much larger distance. For example, I'll talk about the dark energy spectroscopic instrument, DESI. It can see redshifts up to 1.4 or 1.5, basically 10 times of that what Sloan Digital Sky Survey could see in redshift space. And another question he had is, if something is very far away, the visible light that has been emitted by that object will not be visible in the visible spectra for us. So essentially what we are seeing is not when we are observing something using visible lights, it's not actually being emitted by that object in the visible spectrum. So yeah, that's something that we have to live with. When you study the properties of the galaxies, you have to account for this fact that what you're seeing is not actually what is being emitted. And that correction is sometimes called K correction. And yes, you are correct that if something is not being emitted in visible light, we either may not see it, or we are actually looking at the galaxy at a different set of wavelengths in the rest frame. And also, he also asked whether we can measure the velocity of sound waves from baryon acoustic oscillation or not. This is possible because the velocity of sound waves is entirely a property of the material which it's traveling through. So I don't know whether we can measure it directly, but we can theoretically definitely say that what the velocity was, because if you remember from class 12 or so, velocity is entirely a proportion of velocity is entirely dependent on how compressible a material is. So we know that how compressible a soup of atoms and molecules is, and from that we can calculate the velocity. Yes, but so moving on to what we are seeing here is that this image shows a dot. This image shows a projection of what the Sloan Digital Sky Survey sees, and each dot in this picture corresponds to the location of a galaxy. And the color corresponds to the density of objects available. And as you can see, the universe has a lot of structure in it. In the small scales, there's this kind of web-like structure, the cosmic web that people say. And by studying how these structures evolve, or like how the galaxies cluster, uh, you can study a lot about the universe. And this clustering of galaxies and is also a very hot topic currently. And as I was like slightly mentioning, is that now that you have spectra of galaxies, you can also study how galaxies have evolved over time. Yes, you cannot observe the evolution of one single galaxy over a billion years, but what you can do, you can see multiple galaxies at different stages of evolution and join these small pieces of information to make a coherent history of a galaxy. This is similarly very similar to, like, if you want to know how a human being grows up, it might be very hard to observe one single human being over their entire lifespan, but you can just observe all the human beings in a city, and there are people across multiple ages, and by observing different human beings, you can just create a story of how one single human being ages over time. And so if you have information about a bunch of galaxies, you can, using statistics, create a story for how galaxies evolve. Another thing which is becoming very popular these days and will become even very popular in the very near future is astronomy in the time domain. So as I said, you can take picture of the universe, but you can also take multiple pictures of the same patch of sky and compare them to see how the sky evolves with time. There are tons of different phenomena which occur in time, like stars explode. These are called supernova, and using those, you can essentially find distances to objects. You can observe variable stars to study properties of stars. Um, there's asteroids. There are other solar system objects. There's a tons of things that you can do in time domain astronomy. And as I'll show, time domain astronomy is already a very hot topic and will blow up to become very big in the very near future. So I told you what a sky survey is and what a brief overview of different things that you can do using a sky survey. Now the question is, how do you do it? I might have mentioned to you the Sloan Digital Sky Survey, which is a very successful project and have contributed significantly to the evolution of knowledge about the universe. But I want to talk about something which is happening right now, and I am in some way involved with it. It's called the Dark Energy Spectroscopic Instrument, or DESI for short. So we have this male 4-meter telescope in Kitt Peak National Observatory, Arizona. And what this instrument does is that it has this robotic arms kept at the focus of the telescope mirror, and each arm has one fiber optic cable attached to it. So each of these arms can automatically put a fiber optic cable to the location of a galaxy or star um, on the focal plane of the telescope to carry the light from that particular object to the spectrographs, which are basically prisms, which split the light and get the spectrum. And it has 5,000 of those arms. So you can take spectra of 5,000 objects simultaneously. And its main goals are to study baryon acoustic oscillations and the growth of structure. But since you have these massive data sets, you can also study the Milky Way, galaxy formation and evolution, and somewhat of time domain astronomy. So what's the big deal about this new instrument? Like, why does it exist? What's so new about it? So to understand that, let me tell you how spectroscopy was done previously. What you would do is take a telescope like this, and the mirror reflects light to its focus. You will put a metallic sheet at the focus and drill holes at the locations where you expect there to be a galaxy. And I'll show you a video right now. Yes, so this is that process being done for the Sloan Digital Sky Survey, where you have a piece of metal stuck at the focal point of the telescope, and you have manually drilled holes at locations where you expect to be a galaxy. And then someone will go and put a fiber optic cable through that holes, um, through that hole, and then observe. So as you can see, this process is very time intensive and takes a lot of time. What DESI does is replace this whole sheet of metal with a plane where you have these robotic positioners. There will be 5,000 of them. This is just a small cross section of it, where each of these arms have a fiber optic cable attached to it, and they can move in this small region to put the fiber optic cable on top of these galaxies in the focal plane of the telescope. So you do not need holes or metals or anything like that. It all happens in a click of a button. So just to put things into perspective, the Sloan Digital Sky Survey could take the spectra of a couple of million objects over the span of 1 decade, or close to 12 years. On the other hand, DESI plans to observe spectra of 30 million galaxies or 30 million objects in a span of 5 years, which is a huge improvement. And this is a picture of the first light that DESI received, where each of these dots corresponds to the location of a fiber optic cable, and you carry the light from that patch of sky and split it up into its constituent wavelengths. And this action has already begun, and this is a project which is happening right now. But all is well with spectroscopy. You have a lot of information, but there's a problem. The thing is, the very fact that you're collecting light from an object and you're splitting it into its constituent wavelengths means that there's very small amount of light in each chunk of wavelengths. So spectroscopy is a very expensive process. You need bigger telescopes to collect more light, or you need more time to collect more light. So can we do away with spectroscopy? Can we get this third dimension just from images? And as it turns out, we can. So there's this whole industry called photometric redshifts, where you try to infer the redshift of an object just from the images. The methods are quite complicated, but in this picture roughly shows why this method works. Is that in the background you can see there's a fake spectra of a galaxy which is just moved across wavelengths to mimic redshift, and these dots show what is the total flux that you would have received in this chunk of wavelength if you were observing it just using photometry. And as you can see, these small dots move in a particular fashion as a function of the wavelength, or as a function of the redshift. So even though you do not have the spectra, even though you do not have these fine-tuned features in the spectra, just observing the flux that is coming in these big chunks of wavelengths, and these you can infer the redshift of an object, just because there's some kind of relationship, which is a very complex relationship which no one knows, but people try to model this relationship. So with this technique in hand, and currently these techniques are quite advanced, that you can get pretty good redshifts just from images. You do not need spectra. The future is being planned. There's a new upcoming telescope called the Vera Rubin Observatory, and people are planning for the legacy survey of space and time using this telescope. It's an 8.4 meter telescope with 3.2 gigapixel camera, and it can image huge amounts of sky in one frame. So basically, it can image a sky area equal to 40 full moons in one snap. And hence, it can get a picture of the whole sky every 3 nights. And it will do this for 10 years. So now you're not only mapping the sky very fast just using photometry, but you're also mapping how the sky changes over time, and hence the name Legacy Survey of Space and Time. Since this is a bigger telescope, you can see much deeper than what we could see. And there's a bunch of science cases that it plans to explore. And this includes stuff that I was talking about, like studying dark matter and dark energy, cataloging things within our solar system, because we never had such a big telescope looking at the whole sky before this. We can, yes, explore how the sky changes with time, like transient phenomena like supernova or variable stars. And also we can study the structure of the Milky Way. So this is a very brief overview of what has been happening. And as I said, this is what the observatory looked like last month. And as you can see that it's almost done. And it plans to start its observations sometime next year. And many of you probably will be graduating very soon. And a lot of things are happening in astronomy in general and using sky surveys to be specific. So like, as an obvious question, like, should I be excited about all that's happening in astronomy? And my biased opinion is yes, a lot is happening, and there's a lot of scope to contribute to many of these projects, which involve tens of different countries and thousands of people to run them. So the question is, like, that should you do a PhD in observational astronomy? And well, the answer to it might not be very easy. It depends. So let's look into the PhD from a very critical standpoint. Like, let's see why you may not want to do a PhD. And a very simple reason is, like, you don't like research, and that's fine. It's not everyone likes everything else. You might not find pleasure in finding new things out, and that's fine. The two things that I wanted to mention is that just because you're in NISER, you have done a lot of research as part of your curriculum already. And just because you did it as part of your curriculum does not mean that you have to take up research as a career in the future. If you don't like it, you can feel free to not continue doing research. And I believe what you learned by doing research in NISER is not doing research as say, but rather the scientific method of approaching anything. So if you want to be an administrator, the scientific method of approaching stuff will be very important. Or even if you're just a normal citizen, you can apply the scientific method of tackling a problem to decide who you are voting for. Or like, you'll think about judging the WhatsApp forwards that you receive saying 5G causes coronavirus or whatever that shit is. Yeah. So basically, you're learning the scientific method of doing stuff in NISER. And if you don't like research, you don't have to do a PhD. And then there's Indian parents. You have already taken the first step, but by not doing engineering. So kudos for that. But you don't do research just because your family told you or all your friends are doing it. And this is a very sad part of it. In any PhD program, you might be able to sustain yourself very well. But if you have a family to take care of, then you might not be financially stable enough to support a family. You'll always be financially stable enough to support yourself. And you need a lot of patience. Things will be slow. That's Fine. And something which I would like to tell you is that, like, what do observational astronomers do? When you say that I am an astronomer, people will think that you're that crazy guy who goes, stares and looks at stars at the night. And this is probably the least thing that observational astronomers does. So if you are doing research in observational astronomy, what you will be doing is, one, writing a lot of software, mostly in Python. Two, do a lot of statistics. Three, do a little bit of engineering, or like in terms of playing around with electronics on a telescope, or like doing machine learning and things like that. And four, sometimes you might be going to do observations on your own. So the two most things that you will be doing is writing software, writing codes, and two, doing statistics. And you frankly do not need to be a genius to do that. There are a lot of smart people, a lot of smart physicists. That's true. But mostly what separates scientists from everyone else is that they're just stuck with it. They are just like any other normal person you see. They have done 300 mistakes before doing one thing correctly, and you see that one thing they did correctly, and that survivor bias goes into our mind. We never see the 300 things that people do wrong. And you should not think that I am not smart enough, hence I cannot do a PhD. You all are smart enough to join a PhD program by the very fact that you're in NISER. So coming back to the question of why you should do a PhD, and specifically in observational astronomy, and the obvious thing is you like research, you like astronomy, and that's a perfectly good reason to do research as a career, to take up research as a career. The other thing is that you want to be in academia, you want to be a professor, you want to be a teacher, you like teaching, and getting some research experience through a PhD is probably the first step towards becoming a professor. And as I mentioned, that the two most things that you will be doing as a researcher in astronomy are writing software and doing statistics. Your skills will be very easily transferable to the industry. There's this huge industry, huge data science industry that you might have heard of it. A lot of things going on. For example, Google tracks everything you do online and knows you probably better than you know yourself, by mining your data. And this data science is probably the most hot industry right now. And being a researcher in observational astronomy automatically qualifies you to become a researcher in data science, because in day-to-day activities you are doing data science. You are doing data science to study physics, but at the very core you're doing data science, and you'll be dabbling with things like machine learning and all, and which are currently becoming very good things to learn if you want to join industries. So basically what I want to say is that if you do a PhD in observational astronomy, you do have a lot of career options, and which is nice. So what do we need to keep in mind before applying? And in India, the only thing that you need to do well is in that one entrance exam. So I'm hence talking about application processes outside India. The things which are most important are, in decreasing order of their importance, are like GPA, your research experience, and bonus points if it's published, so that you can point towards a piece of material that you have created in your application form. And this, I've written down them one after another, but these are like equally important. You do not need to have a stellar GPA and have done publishable research, but if you are decent in both of them, you're good. Or even if you do not have a very good GPA and have done good amount of research, that's also good. You just have to be good in one of them, or uh, slightly good in both of them. So, and then this is the obvious thing, you need good letters of recommendation, and it will be better if you can manage to get the letters of recommendations from people who are famous, or from people whom the admissions committee know personally. And that ties down to the next point, where carefully selecting where you apply makes a lot of sense, because one, the application process is expensive, and second, if two people write you equally good recommendation letters, just because the admission committee knows someone personally, will have a higher weightage. That's why if you apply to places where the person you're working with did their PhD or postdoc or just has collaborators, makes more sense than applying at a random place. And it's always recommended to contact a faculty member, because what happens, and something which happens often in physics and astronomy department, is that in one year there were too many people who wanted to do astronomy, and hence there's just not enough space available to take new astronomers. These kind of information is not given out to the public, and it might be the case that for a particular year the university is actually not even looking for any astronomy student, but you have applied, and even if your application is very good, you will not be accepted just because they do not have space for it. So it's always good to contact a faculty member just to know that there's space for more astronomy people, or just to build up a connection with that place where you're applying. So contact a faculty member before you're applying to that place. And good communication skills always help, um, but it's not the single most important thing, as you see. And last and definitely the least is GRE and physics GRE. So what has happened recently is that there's enough research, data-driven research, which shows that your score in physics GRE is absolutely not correlated with your success in grad school. And you can look up papers there are there. So what they say is that that one exam, which there are plenty of chances of you screwing up, does not determine how well you do in research. And the things which correlate well with your success in grad school are things like GPA and how much research you have already done. And hence most universities now have stopped asking for physics GREs, and almost all of them have made it optional. So physics GRE should be on low on your priority list, and there's a fair chance that when you're applying, this university won't even ask for a physics GRE. General GRE is also being phased out recently. If some of the schools have started phasing out GRE, they do not require any form of GRE, but still general GRE is mostly required as of 2020. But still, the importance on GRE is getting decreased day by day. And some of you who will be graduating in 2 or 3 years, GRE may not be a thing then. Um, so that's what more or less what I had to say. Feel free to chat with your questions, comments, concerns. Okay, I'm reading through the questions on the chat then. Okay, so the first question is from Dukisham Bhaiya saying, is dark energy the causes expansion of the universe? That's kind of true. The universe, as we see, is expanding even if there's no dark energy. What dark energy causes is the dark energy causes the expansion of the universe to be in an accelerated fashion. So dark energy causes the expansion of the universe to become faster and faster with time. Even without dark energy, the universe will be expanding, and that's what people believe right now. And the thing is, and then the second question was, how do we detect or prove the existence of dark energy? So a very simple method is like, if you measure the distances to different objects using whatever method you have, as a function of redshift, you can say have an independent measure of the distance, which is not independent measure of a distance to an object, which is not a function of a redshift, versus the distance measured to an object, which is a function of the redshift, and compare those, and you'll find a discrepancy. And hence, you'll see that redshift is a measure of how much the universe has expanded. And if you have an independent measure of the distance, you'll see that there's a discrepancy, and that discrepancy hints towards the existence of dark energy. The another question is how baryon acoustic oscillation helps us to understand the nature of dark matter. Baryon acoustic oscillation can help us understand how much dark matter there was in the past. I don't know how well it can explain the nature of dark matter. People are trying to understand them through more sophisticated or more direct ways, where people are trying to make detectors which are intended to detect dark matter directly. But yes, by measuring baryon acoustic oscillation, we can definitely say how much dark matter that is. And there's another question is, what is the smallest telescope that you can use? There are tons of telescopes. Like NISER has a pretty good telescope right now, which can, given enough time, can see a lot of sky. And there are larger telescopes than 8.4 meter right now. But what the speciality of LSST is its field of view. There's no other telescope which can see a huge sky area right now. LSST has the largest field of view right now. And that's the specialty. There's another question is that you love math, and what is the role of mathematics and astronomy? Well, quite a lot. If you're doing theoretical astronomy, then you will be doing a lot of math, just because math is just the language in which we write physics. If you're doing observational astronomy, you might not be using all of math, but you will be using a lot of statistics and machine learning, things like that. So you'll be using a lot of applied math in observational astronomy. And statistics is math, probability and statistics. You'll use that kind of applied math. But yes, if you're doing theoretical astronomy, you will be using math heavily, just because math is the language in which people write physical laws. What are the most emerging fields in astronomy and astrophysics? Well, this is a very tough question, but there's a lot of good things that are happening. One is, yes, you might have heard, there's a lot of happening in the field of gravitational waves, and India is going to be a big part of it. So gravitational waves is definitely a very emerging field. And another thing is, yes, the science using surveys like LSST, which are coming up in the next few years, like, for example, time domain astronomy, where till now we have found out at like in order of a few thousand supernova, but LSST promises to find thousands of supernova each night. So time domain astronomy is probably going to get revolutionized in the next few years just because of LSST. So it is probably another huge field, upcoming field. Um, do summer winter schools really matter during master's admission in Europe? Well, you can probably club them club them under your research experience. Probably they do not matter a lot, summer winter schools, but if you have done research, that probably counts more. And master's admissions in Europe direct you're eligible for PhD directly in Europe too. So you do not have to do another master's in Europe, for example. Um, and the person wants to know things like, how do you learn data science and all, even if these are not being taught in NICE? That's a good question. You can actually learn a lot because our math department floats two courses, one on probability and one on statistics. These are data science. So from a personal point of view, the probability and statistics course for us both were taught by Shamul Krishna Desar. These were one of the most important courses that are being used right now. Probably those two courses are more useful for me now than most of physics courses, basically. So even in NISER, you can take probability and these two courses on probability and statistics and get the foundations for data science going on. And after that, if you want to learn how data science intersects with computer science in terms of machine learning and deep neural networks, you can feel free to learn them from online courses such as Coursera has a very good set of deep learning courses on deep learning, which you can do, which are pretty good. So Coursera, EDX, these are pretty good stuff. And if our School of Computer Science comes up with courses on machine learning, that'll be also great. Yeah, but you should feel free to take courses on probability and statistics, which are already being offered in NISER, and then go on to learn machine learning and stuff from all EDX and all. Pulkit asks that in a PhD, it often depends upon the relation between you and your guide. How to think about managing this factor when applying for a PhD? That's a good question, actually. It's true in PhD, a lot is dependent on your relationship with you and your guide. One thing you can do is that if there's a university, when you're applying, you look at the faculty list and then look and make a subset of professors who you would want to work with. Um, so if there's no one in that university with whom you would want to work with or whose research does not interest you, do not apply to that university. Just because of this university is famous doesn't mean that you have to apply to it, or you'll be a good researcher if you go into that university. So while applying, you should do a survey of the people who are in that university and and list down a subset and of the people who you would want to work with, and you can write the names of these professors in your application that I would want to work with these professors. So this takes care of the research aspect of the professor, but still you won't know whether you will work well with the professor from an interpersonal point of view, and nothing can be done with it about it really before going into the university. It might be that the research that professor is doing is something that you like, but you just do not like the professor as a person. Uh, so generally what happens in US is that you can easily switch between professors once you are in a graduate program. Even if you say that in your application that you want to do astronomy, after you get into the college you can feel free to um, move to other branches of physics. No one will stop you from doing so. Similarly, you can also feel free to switch from one professor to another professor. Just because you worked with a professor for 1 year and then after that didn't like that person, you do not have to stay with that person. Things in Europe are a bit different because you do not get admitted to a university run program. Rather, you get admitted to the research group of a professor, and then it's pretty hard to uh, switch professors in Europe. The better way would be to, if you are selected, to have a video chat with that professor and talk to them personally before telling them your decision of joining or not. That might be an option. But in Europe, yeah, switching professors is a bit tough. Abhijit says, what is the best way to measure lambda according to you? So I'm assuming by lambda you do not mean wavelength. You mean the cosmological constant, or what we think might be dark energy. So there are, first of all, the question is dark energy the cosmological constant? And coincidentally, just yesterday, I was listening to a talk where people were arguing that dark energy may not be a cosmological constant, or rather, dark energy changes with time. Uh, so, given the situation that we do not know what the nature of dark energy is right now, I have no clue whether there's a best method to measure it right now or not. But there are things like baryon acoustic oscillations can help us map dark energy as a function of time. For example, if you find that BAO peak across different redshift ranges, from that you can figure out how dark energy was at different points of time, because the farther you look in redshifts, you're actually also looking farther back in time, because light takes a finite amount of time to travel to you. So BU is a nice method. Supernovas are also a very nice method to find distances to objects and hence infer things about dark energy. I don't know whether there's a best method or not, and even whether dark energy is lambda or a constant or not. A cosmological constant means that dark energy has been a constant thing throughout the evolution of universe, but people are still arguing whether dark energy is a constant throughout the evolution of universe or not. It's up in the, yeah, who knows. Renuka asks, how much does the BSc diploma in data science provided by IITM online will be helpful for observational astronomers? Well, I don't know how much it will help you in terms of getting into a PhD programs, but you will learn stuff, right? So it will provide you a good foundation to do observational astronomy, regardless of its value in applications or not. Uh, so it's, if you do an online program, it's good. You learn a lot of stuff, and having a degree and learning data science is probably very helpful, because then once you go to a PhD program, you do not have to spend a lot of stuff, learning the tools, you can just start doing research immediately if you know those tools beforehand. And of course, I think if you have a degree online, it might help you to get into a PhD program also. Yeah, it's always good to do if you have time, because coursework in NISER is already pretty heavy. So if you have time to do stuff, great, you should do it. But don't take too much stress because NISER's coursework is already very heavy. Ajay asks, can you tell more about observable and unobservable universe? How are they precisely estimated? Well, observable universe means that the distance which light could travel in 14 billion years or so. So that's what an observable universe is, the farthest distance that light could have traveled in 14 billion years. Unobservable universe is anything which is farther away from that, and it's unobservable. And there are tons of theories of what lies there, but who knows? Because I don't know whether we will ever know or not, because it's beyond our capabilities of observations. Um, how are they precisely estimated? And as I said, like, the precise estimation is basically if you find how much light can travel in 14 billion years, which is not equal to 14 billion light years of distance, because the universe has been expanding in the meantime. So this distance is actually way more than 14 billion light years. Renuka asks where one can find astronomy projects. That's a good question. You can do your summer internships at places where they have astronomy faculties. You can mail people, directly go and look into the websites of organizations like IUCA, TIFR, IIA, um, Aries Nainital, and places like that. Even if you're in first year or second year, you can even do research in NISER itself. In your senior with Tuhin sir or Nishikant sir, you can mail professors who work in astronomy in other ISERs or IITs. IIT Indore has a very good astronomy group. Uh, Many of the ISERs have pretty good astronomy groups. So you can mail professors directly. And some of the ISERs have summer programs too, and you can apply for the summer programs. Indian Academy of Sciences have a summer program. There are quite a few international summer programs which you should apply to. These are like MyTax, which is a summer program in Canada. Then there's European Southern Observatory has a summer program. Then the Netherlands Astronomy Astron, which is the Dutch Radio Astronomy Research Institute, has a summer program. So you should also look into the summer programs which are outside of US. Outside of India. But the simplest thing would be to just find out professors and just mail people that, are you open to taking a student this summer? Abhijit asks, as Pulkit Bhaiya said, can you give any tip to find how a guide going to turn out, and also any good source to read about BOA? Yeah. So how the guide will turn out from a personal point of view, not a research point of view, is hard. One thing you can do and you should do is, let's say, before applying to a university, you had decided that you want to work with these two people, one of these two people in that university, and that's the reason you applied to that university. And now you got an acceptance. So since you have an acceptance to the university, you can mail the professor who you specifically want to work with and have a video chat with them. And from that video chat, you can figure out how that person is. or not. And if you have this option that you have been accepted into multiple universities, then you can compare between different professors and then accept the offer. But yeah, knowing how you will work with the person in the long term is pretty hard, and I do not know whether um, there's a method to finding it out before you join the program. But yes, if you join a program in US, you have a good amount of flexibility in switching guides. Um, you can easily switch from one person to another, or even from one research field to another research field. That's perfectly acceptable. Things might not be as easy in Europe because the system works in a different way. But yeah, you can video chat with people, and if you have an acceptance to the university, then the faculties will be very happy to talk with you. If you're just a random person looking around, people might not be willing to give you their time. But if you have an acceptance to the university, feel free to set up a video chat with the professor. And also, any good source to read about BOA, if you are in fourth year or fifth year, you already have enough physics or mathematics background to understand the intricacies. So if you're in the fourth year or fifth year, you can take up any cosmology book, and they will cover BOA. Uh, Scott Doddleson's new book. Scott Doddleson has a book on cosmology, and he has a new book in cosmology, which is a pretty good book. Um, I am biased toward that book because he taught our cosmology class, but it's in absolute terms a good cosmology book. You will have enough mathematical background to understand things in that book if you are in fourth or fifth year. But if you are in like the first, second, third year, you might not have enough mathematical background to study things in that detail, and you can uh, take up any introductory astronomy book. Like, I had a book lying around like this is astrophysics in a nutshell, which is a good book. Or you can read about stuff from that big orange book, which you probably all follow to do your lecture series. The brand. Sorry.
Nosli.
Yeah. Osley and someone else. Yeah, that big orange book, basically. Yeah, you can, if you're in first, second, and third year, you can study things from an introductory astronomy book, and you'll probably get to know stuff that. Uh, Pravanjan says, is it wise to seek to fields of astronomy and astrophysics which is often treated as fictional because there is not really any physical entity to do research on, for example, existence of wormhole and higher dimensional physics which only have wild theories as backbone? Uh, I do not think there's, if you do, I do not think you can do a PhD on these wild theories of wormhole and things like that. Higher dimensional physics is a real thing. People in string theory treat that universe has a lot of other extra dimensions, and this is a real legitimate field of research which you can work on. Um, and you can feel free to work on them even in your undergrads. But things like wormholes and all, uh, wormhole is probably a very media friendly topic, but there are things like applications of general relativity, to study these kinds of phenomena. These are things that you can do. So there are legitimate versions of everything you said, and you can do research on it. So and if you like them, you can do it. uh, how to use this log9 time to learn more about astronomy? Hmm. First of all, yes, stay safe in the lockdown. You're not obligated to learn new stuff during this lockdown. But yeah, if you want to learn new stuff, you can read a book about astronomy, as Akshay also mentioned in the chat. Carol and Ostley, uh, that big orange book is a pretty good reference. Or if you do not like reading books, and that's a personal preference, you can do online courses. There are very good online courses on introduction to astronomy on edx or Coursera. There's a series of astronomy courses on edx taught by Brian Schmidt, who is a Nobel laureate, and you can find and those courses are very good. I had seen them when I was in second or third year. um, you can do those, and those are pretty fun and do not require a lot of advanced stuff. uh, you can do online courses or read a book. If you It's a personal preference. Some people like to read books, some people do not. So whichever you like, it's good, up to you. um, Also for fun, as I had mentioned, that before you have joined observational astronomy as a research career, you would think that doing astronomy is all about looking through telescopes, but in reality, that's the least amount of stuff people do. What you can do is, there's a lot of citizen science projects going on. Uh, you can look up Galaxy Zoo or zoouniverse.com, or join other citizen science projects. One NISER had a workshop on one of them called what, Rad at Home and the Hotas. Rad at Home, you can participate in those. And those are pretty nice avenues to learn astronomy from. Um, and also learn a little bit of programming. Do a online course on Python. Learning programming will always be a good skill, regardless of you doing astronomy in the future or not. You will need to know programming in any form of research that you do. Um, so learn Python. Python is a nice language. Uh, you can do you can learn them from books, or again from online courses, as you wish. So do you have any other questions? Yeah, and you're welcome, Renuka. Yeah.
Okay, so I think we should wrap. Okay, so thank you everyone for joining us, and a special thank to Biprateep Bhaiya for giving his time. Shriram is also thanking you. Okay, okay Bhaiya, thank you. We hope